In this research, OpenAI is researching how less intelligent humans are going to control more intelligent superintelligence. They are doing that by controlling today's GPT-4 with GPT-2 level model to simulate less intelligent model controlling more intelligent model. They are using reinforcement learning from human feedback, and they are generating labels with GPT-2 level supervisor model, and they are applying those labels to GPT-4, and they say that they can get GPT 3.5 level performance. This means that they successfully controlled higher intelligence model with lower intelligence model, but they didn't get the full capabilities of GPT-4. So they are also saying that reinforcement learning from human feedback will scale poorly to more intelligent models. They start by saying if Superhuman assistant model generates millions of lines of extremely complex computer code, humans will not be able to provide reinforcement learning from human feedback on that complex code. Whether the code follows the user's intentions, whether the assistant model answers questions about the code honestly, whether the code is safe or dangerous to execute, and so on. To study this, OpenAI is going to use weak models to supervise strong models. The first question they ask is, why should weak to strong learning be possible? For example, when a weak supervisor is teaching the strong model can just learn the same errors that the weak supervisor is providing. But on the other hand, the strong model should already have the knowledge that the weak supervisor is trying to teach them. For example, is the code ethical or honest? The weak model just needs to tell the strong model to teach the strong model to make the code ethical. But it doesn't need to teach them how to make the code ethical, because the super intelligence already knows how to do it. So this is what gives them hope. OpenAI took pre-trained only GPT-4 model without the fine-tuning and fine-tuned it with data generated with a GPT-2 level model. And these are the results they got. Here they did 3 experiments. We're going to talk about these experiments later, but here are the results. First, this is the weak performance on these 3 experiments. So we have representative NLP task, chess puzzles, and ChatGPT reward modeling. So weak performance is the performance of the weak supervisor, the GPT-2 level model. You see the accuracy is only a bit over 60%, around 30%, etc. And the big gray line is the strong ceiling performance. So this is the properly fine-tuned GPT-4 model. It has the best performance. Now these 2 middle lines, they are GPT-2 fine-tuning GPT-4. So they used multiple methods for each of these tasks, and naive reinforcement learning from human feedback. This is the results when you use reinforcement learning from human feedback by GPT-2 generating reinforcement learning feedback for GPT-4, you get these light blue results. And the purple results are the best method used in each of these examples. So they discovered a specifically best method for using GPT-2 to train GPT-4. And we're going to talk about these specific methods later, but they also improved the performance as well. There are 3 things they learned from this. Strong pre-trained models naturally generalize beyond their weak supervisors. So if you use a weak supervisor just to generate labels for GPT-4, the GPT-4 is going to perform better than the GPT-2 that generated labels. But it still performs worse than training GPT-4 on ground truth. That is, fine-tuning GPT-4 on ground truth as opposed to fine-tuning it on GPT-2 generated labels. So that's why the generalization will scale poorly to superhuman models without additional work. And at the 3rd point, they are saying there are some tips and tricks in which you can improve the generalization of GPT-4 training with GPT-2 level model. But here's the disclaimer, all of this is just a proof of concept and it sometimes works, sometimes doesn't work. So we need more research. With a lot more research and progress, we can actually, for example, develop a superhuman reward models or safety classifiers, which we could in turn use to align superhuman models. The methodology they are using is, first they train a small weak model on ground truth labels. Ground truth labels are just the truth. The problem is that in superhuman intelligence, humans will not be able to provide ground truth because intelligence will be a lot smarter and the problems will be too complex. But now we can provide ground truth labels, so we create a weak supervisor with ground truth labels. Then they train a strong student model with weak supervision, so they just generate the labels from that weaker model. They are not ground truth labels. And for comparison, they also train the strong model with the ground truth labels. They call this strong ceiling performance. Intuitively, this should correspond to everything the strong model knows, i.e. the strong model applying its full capabilities to the task when trained on ground truth labels. They introduce a new metric, performance gap recovered. This is basically, if we have weak performance of the weak model and strong ceiling performance, the perfect performance of the strong model, how much performance can we get with weak to strong generalization? So this is the formula, weak to strong minus weak over weak to strong, strong ceiling minus weak. So if we have a perfect model, perfect weak to strong performance, that means the PGR will be 1 because we will be here at this line. Or if the weak to strong model does no better than the weak supervisor, then PGR is 0, then we will be here. Now we will take a look at the results they got. So we're gonna take a look at these graphs. Let's first take a look at NLP tasks. The y-axis represents test accuracy. First we will look at this straight line that doesn't have any dots. This is strong ceiling performance. So this is basically GPT-4 performance without any GPT-2. This is just the vanilla GPT-4 performance. On the x-axis, we can see this is the percentage of GPT-4 compute we have. So at 1, we have 100% of GPT-4 compute. So GPT-4 model at 100% of GPT-4 compute, it's gonna score around 90% test accuracy on NLP tasks. But as we move to the left on x-axis, we can see that it goes up to around 10 million times less, 1/10 millionth of the compute of GPT-4, and we can see that GPT-4, this line scores around 63% accuracy on 10 million times less compute. So this is the test accuracy as a function of strong student size, of the GPT-4 size. But these different colors, they basically represent the size of the teacher, of the weak teacher model that was training them. Here, the strong student model, this yellow line that's trained by the biggest weak teacher model, is closest to the baseline ground truth GPT-4 model. As we increase the size of the GPT-4 model, there is more difference between the ground truth model and the GPT-4 models that are trained by weak supervisors. And as we decrease the size of the model, if we move to the left, they are more and more similar to the weakly trained supervised models. OpenAI says this is a decent weak to strong generalization in NLP tasks. Here we have performance gap recovered against size of the model, and this is positive scaling of that performance gap recovered. Here we have good generalization for chess puzzles, but performance gap recovered has negative scaling, As we increase the model size to the right, we see that the performance gap recovered is getting decreased. So this is negative scaling, this is bad. Now for ChatGPT reward modeling, OpenAI says this is poor generalization. To me, honestly, it kind of looks similar to NLP tasks. I guess it's a bit lower generalization. I'm guessing that's why they call it poor. And this is horrible. This is going into negatives. Performance gap recovered is going, this is horrible. This is very bad. Even for the strongest compute, 0.1 and 1, here if the yellow line, they are recovering only 20% of the performance. So this is not good. And for other models, they are only recovering about 10% on average here. But the conclusion is that strong students consistently outperform their supervisors, and there is hope that this is a tractable problem, so it can be solved by more research. There is another method, it's bootstrapping. Basically, instead of directly aligning very big superhuman models, we could first align only small superhuman models, use that to align even bigger, smarter models, and so on. Now, if we take a look at their experiments with bootstrapping, and this is only for chess puzzles, so the dotted lines are our previous results with naive, just weak to strong performance, and then these lines with squares are now bootstrapping models. So we can see that on average, bootstrapping performs better than just naive weak to strong training from our previous graphs. And this is PGR with bootstrapping. So here we can see that taking multiple small steps in training, then rather than one huge step, actually leads to better performance. We can see here that these lines are actually a lot more like going a lot higher. Now, if we increase the model size completely to 100% of the strong student GPT-4 compute, then looks like the naive training is a bit better, but otherwise most of these bootstrapping graphs are going up and higher than the naive strong to weak training. Here they speak about constructing a sequence of models M1 goes to M2, etc. to Mn of increasing sizes. Then we use the weak labels from M1 to fine-tune M2 and use M2 to generate new weak labels that we could use to generate the next model and so on. But even though bootstrapping worked for chess problems, they only noticed small improvement in NLP tasks and no improvements on the reward model setting. The conclusion is bootstrapping should be looked at and researched more, but naive bootstrapping alone will not be enough to align models much smarter than their supervisor. And auxiliary confidence loss can dramatically improve generalization on NLP tasks. And guys, whenever I say naively fine-tune, that means this is reinforcement learning from human feedback fine-tuning, but instead of humans providing feedback, GPT-2, the way weaker model, is providing feedback. That's what means naively fine-tuning. Now, what this auxiliary confidence loss, basically the researchers want the smart GPT-4 model to be confident in its knowledge. So if dumber model gives it some false information, the GPT-4 model should actually listen to its pre-training and to what it already knows, and it shouldn't learn the incorrect information provided by the smaller model. But at the same time, they want the GPT-4 model to understand the intuition and the intention of the GPT-2 model, so believe itself on the information, but understand what the GPT-2 model wanted it to do with that information. They are calculating this loss with cross entropy between the probability distributions of the predictions of the weak model and the strong model. Here we can see substantially improved generalization on NLP dataset with a simple auxiliary loss. Dotted lines are our naively trained models, and lines with triangles are models with auxiliary loss. We can see that models with auxiliary loss are hugely outperforming naively trained models, And this is especially true for the models that are trained with smaller teacher models. And also, as we increase the size of the student model, we see the bigger difference in performance with auxiliary loss. If we take a look at the PGR graph, we can see that the biggest improvements are when a large student model right here is trained by a small teacher model. So these are the bluish lines, the small teacher model, and we can see huge increases in performance here. So to train auxiliary confidence loss, they just add auxiliary confidence loss term to the standard cross entropy objective while fine-tuning the pre-trained GPT-4 model with the weaker teacher. So this new loss term is gonna reinforce the strong model's confidence in its own predictions, even when the big model is disagreeing with the weak labels. Auxiliary confidence loss works best if we train big student models with small teacher models. So here this is our naive training right here, and this line goes actually to 80%. It's 25% versus 80% if we use auxiliary loss. But if the gap between compute power of the student model and compute power of the teacher model is small, then auxiliary loss performs worse. They also note that confidence loss improves on most NLP datasets dramatically, and for many datasets we get almost perfect generalization, recovering nearly all the performance of the strong model even when using the smallest weak supervisors. Also, they find that the auxiliary loss reduces the strong student's imitation of weak errors and mitigates weak label overfitting. They also found that larger student models consistently agree less with the errors of the supervisor than smaller student models. Pre-trained models may have a hard time fitting errors of other smaller pre-trained models. That means if the smaller model is trying to teach the bigger model something false, the bigger model has trouble learning it because it believes it's false. They also talk about how some errors are easier to imitate than others. So if the error of the weak model is hard to imitate, then the strong model is gonna be less likely to make that same error. Weak to strong generalization works better if the concept that we are trying to elicit is already well understood by the bigger model, because then it will not imitate our mistakes about that concept, but it will draw from its well understanding of that model, of that concept that is. They also explore eliciting strong model knowledge with prompting. They found that test accuracy improves drastically for larger model sizes when using prompting. So again, the black full line is just GPT-4 model trained on base truth, and these other lines are GPT-4 model trained by a smaller GPT-2 level model. But on this graph we can see that smaller model when with prompts. So as we increase the model size of the strong student model, we can see that the prompted student models are reaching the ground truth GPT-4 model. Here we can compare our three methods. So the dotted lines are just naively trained weak teacher trains strong student, and then dotted lines with X's, the same thing but also with prompts. It's 0 shot to 5 shot prompts. So in prompts they got up to 5 examples. They perform a lot better with prompts than without prompts. And then these lines with triangles, they are naively trained. So the weak teacher teaches strong student with confidence loss, without prompts, with confidence loss. So they perform better than ones with prompts. Now we enter the last part of this paper. It is discussion. First of all, superhuman models may easily imitate weak errors. future models will likely be very good at predicting what humans will think and say, especially if they are trained on human data in a similar manner to current models. Consequently, if we fine-tune it on human supervision, it might just perform like a human and it may not incorporate its latest superhuman capabilities. They also mentioned that even though their strong models imitate errors of weak models, they are not explicitly pre-trained to imitate weak models. But when we train superintelligence, it will be explicitly pre-trained to imitate humans. So it will be explicitly pre-trained to imitate human errors as well. So that might be additional problem. And at the end, they discuss the future work. What would convince us that we have a solution to superalignment? This is a complicated question and we do not claim to have a complete answer. However, we expect substantial progress in at least the following three areas will be necessary: analogous setup, scalable methods, and strong scientific understanding. Thank you for watching this paper review and subscribe.